this week we're going to finish up talking about rational functions. So remember that rational functions are functions that have variables in them. Sometimes we just have a constant with a variable. You can have more than one term in the top and the bottom, like the second fraction has two terms in it. But you got to have fractions. Okay, that's what makes them rational. So we're going to look at some different rational equations. And by the end of today, we're going to be solving questions like that. So we're going to start with a word problem where we're going to make up our own equation. We'll solve it, and then we'll look at some other ones after that. Okay? And the last thing we're going to do is on the graphing calculator, we'll look at rational inequalities. That's all graph on the calculator. So again, we're going to start out doing some stuff algebraically, and then the last thing we do will be graphical. We're going to start with a word problem, but there is a formula that you need to already know to do it, and that's the distance equals rate times time formula. So if you want to figure out the distance that you traveled, you multiply your rate of speed by the time. So we're going to use that formula in the first question, and I would definitely write that down in case you see something with that on the test. You could have that on your reference sheet. Does everybody have the top part? So in our problem, what's going to be happening, we're going to have a person that's going to be taking a trip, and they're going to use two different modes of transportation to get where they're going. So the first part of the trip, it says Sue drove, again this is by car, 30 miles to a train station. And then from there got on the train and completed her trip. In all, she traveled 120 miles. We don't know the exact speed of either the train or the car, but we do know that the average rate of speed of the train is 20 faster than the car. So we want to set up an equation that's going to represent all of that. And the goal when we're done is to have a formula that we can plug into that will calculate the time it's going to take for her to do the trip. Now, what is it that we don't know that's going to affect the amount of time it takes for Sue to complete her trip? Yeah.
The speed of the car.
The speed of the car, and what else don't we know? Yeah.
How far from the train station to where she went?
Well, we're going to assume it's instantaneous. When she gets out of her car, she's instantly on the train and moving. We won't assume that she takes 7 minutes to walk from her car to the train. But yeah, realistically, there would be a little bit of time there. So we don't know the speed of the car, and we don't know. Yeah.
How long it takes, the time, we don't know how long it is.
Well, that's what we're going to solve for, but there's two things that are going to affect that. The speed of the car and,
Speed of train.
the speed of the train. So we don't know the speed of either vehicle. We just know that the train is 20 faster than the car. So we have to pick a variable to represent one of those two. We're going to let our variable represent the speed of the car. So we're going to find an equation that represents the time it takes for her to do this trip in terms of how fast the car is going. So when we're done, you could just give me a speed, like the car is going 50 miles an hour. I'll plug it into a formula, and it'll automatically give me the answer for the time it takes to do the trip, this whole trip. All right. So we're trying to find the total time. How many modes of transportation is she going? Yep.
Car.
Car and train. So the total time that it's going to take is going to be equal to the time she spends in the car. So we'll do the time in the car. Plus, we need to also find the time she's on the train. That's the general idea for the total amount of time. It's how much she spends in the car and how much she spends on the train. Now, we have a formula to calculate time. There is a variable for time in that formula, but right now that formula is for distance. What would we get if we solve that formula for t? Yep.
Time equals distance over rate.
Time equals distance over rate. So if we can find the distance that she travels by car and the speed of the car, then we know how much time she spends in the car. And same thing for the train. If we can figure out the distance she travels by train and the speed of the train, then we know the time she spends on the train. So we need the distance and we need the speed for the train and the car. All right, so let's make a chart. Let's do the car, train, and then we're going to have the distance, and we're going to have the speed. All right, let's start with the distance that she travels by car. Do we know that?
Yes.
Yeah, what's the distance she travels by car? 30 miles. Let's look at the speed. We might not know a number for the speed, but did they tell us a way to represent the speed? Yeah?
Miles per hour.
I'm thinking more of a, not a unit. Yep.
R.
I don't think they gave us a letter R anywhere in the word problem.
So I guess.
Yep. X. They said let X be the speed of the car. Okay, so X is the speed of the car. We don't know it, but we do have a way to represent it. Let's go to the train. Do we know how many miles she traveled by train?
Technically, yes.
Yeah, how many?
90.
90, because she did a total trip of 120. 30 of it was by car, so the remainder of the trip was 90. And how could we represent the speed of the train? Yeah?
X plus 20.
Right, we don't know what it is exactly, but we do know it's 20 faster than the car. All right, so now let's fill in that information to see if we can find the total time for this trip. All right, so let's start with the time that she spends in the car. Time is distance divided by rate. So the distance in the car is 30, and the rate of the car is x. That's the time that she spends in the car. 30 divided by x. We just need to know what x is. How would we write down the time that she spends on the train? Yeah?
90 over x plus 20.
Right, it's the distance on the train, which is 90, over the speed of the train, which is x plus 20. And there we go. So that is a formula that would represent the total time it takes for her to do the trip. So now if you tell me she drove 50 miles an hour, I just fill in 50 for x, do it out, and I'll get how much time it takes to do the trip. Any questions on that equation? All right, so now we're going to we're going to do some things with it. Some of the things that we do will just be algebraic. We'll kind of forget about the word problem for a minute, but then we will come back and look at it in the context of the word problem. Now, if we're thinking of it in terms of a word problem, x is the speed of the car. Practically, that means x could only be as small as what number?
0.
Right. It can't go any lower than 0. Okay. And the dependent variable, the y, is time. Time can't go any lower than y.
0.
Can't go lower than 0. So no negative time, no negative speed. Right? When we're thinking about it in terms of a word problem. Okay. For a minute, forget that this is about a word problem. Okay. So if we get a negative answer for x, for what we're about to do, it's okay. Okay. We're just looking at this as an equation. Has nothing to do with driving a car right now. Just an equation we're going to solve. All right, so they want us to find a few different things. Well, first thing we should do is we should take these two fractions and put them together. What do you need to make sure you have if you want to add two fractions together? Yeah?
Common denominator.
Right, you need a common denominator. And if you've got something like that, you want to add those up. One way that you can find a common denominator is just, actually, let me just change this. Let's do something different. Let's do that. To find a common denominator, you can just multiply the denominators you have together. What would be the common denominator if I'm just adding these two fractions?
28.
28. In order to get a common denominator of 28, what does the top and bottom of the left fraction need to be multiplied by? 7. This fraction gets multiplied by the other denominator. And what about top and bottom over here? 4. This fraction gets multiplied by that denominator. We're going to do the same thing with letters. No different. What do you think the common denominator will be here? Yeah?
X squared plus 20x.
Yeah. It's going to be the product of these two denominators. X squared plus 20x. And what would you have to multiply top and bottom by here to get the common denominator? Nico?
X plus 20.
Yep, x plus 20. So x plus 20 over x plus 20. And what would you multiply top and bottom by over here? Just the x. Okay. So when we do out the bottom, we have x times x plus 20 in both. That's the common denominator. When you multiply the top by x plus 20, you have to distribute it. What's 30 times x plus 20? 30x plus 600 plus, what's 90 times x? 90x. And when you combine your like terms, what's 30x and 90x? 120x. So there's a version of the equation we came up with originally, but this time it's got common denominators. The reason I did that is because some of these things that they want us to find, it's easier to have these two things together as one fraction. For some of them, having two fractions would be fine. Let's start with the EBM. How do you find the EBM of what's in that black box?
The first two terms.
In this case it will be, but in general you're looking for what? Because they might not always be in that order.
Highest is it coefficient?
Degree.
Degree.
Highest degree term in the top divided by highest degree term in the bottom. If it happens to be the first term, great. If not, then whatever term it happens to be. What's the highest degree term in the top?
120x.
120x. And what's the term with the highest degree in the bottom?
X squared.
X squared. And when you reduce that, what do you get?
120 over
120
x.
over x. So that is our EBM. Now we can use that to find the horizontal asymptote. Does anyone remember what you let x approach to find your horizontal asymptote? Yep.
Negative infinity.
Negative infinity or infinity. Yep. You let x get bigger and bigger and bigger, and you tell me what happens to what's inside that box. Okay. Horizontal asymptote. How does the letter of a horizontal line always start?
Y.
Or the equation of a horizontal line? Y. Now, as x gets bigger and bigger and bigger, the bottom of the fraction is getting bigger and bigger, but the entire fraction is approaching what number? 0. Yeah. So we're going to have a horizontal asymptote at 0. Okay, so we've got our EBM. We've got our horizontals. Let's find we didn't do any vertical asymptotes yet. How does the equation of a vertical asymptote start? X equals. And the vertical asymptotes are the numbers that would cause the denominator to come out to what? 0. For that, it's easier to go back to the original rather than the combined one. Does anybody see a number you could plug in that would cause you to divide by 0? Yep.
For both of them or just
Dividing by 0 anywhere. Could be
negative
anywhere.
20?
Negative 20. Yep. And I know negative doesn't make sense for speed, but forget that x represents speed. So x could be negative 20 or 0. Yep. So there are two vertical asymptotes. Okay. So what else do they want? We've got EBM. And the zeros, or the roots. What's another name for a 0 when you're thinking of it as a graph? Which intercept? Yeah, you're looking for the x-intercept. It's where it crosses the x-axis. So let's find the zeros. So the zeros are the x-intercepts. If you have a point on the x-axis, well, every point on the x-axis has something in common. Today, what does every point on the x-axis have in common?
Y equals 0.
The y value is 0. Yep. So in order to find the x-intercept, you take your formula and you plug 0 in for y. All right, so this one, it's going to be easier to look at the second one. Where's my y? I don't see y up on the board at all here. Yeah?
T of x.
T of x. That's my y. Y equals, and now we have that equation on the other side. So it's y equals 120x plus 600 over x squared plus 20x. Okay, so set that equal to 0, and that is how you find your x-intercepts, or your zeros. When you set it equal to 0, you have a fraction equal to 0. How can a fraction equal 0? There's only one way that can never happen. Yeah?
If it's also 0.
Well, that's my question. How do you make a fraction 0? Yeah?
By dividing by 0.
No, if you divide by 0, that's undefined.
You multiply by 0 on both sides.
So could you give me a division problem that comes out to 0? Any division problem.
0 divided by 0.
No, we can't divide by 0. Dividing by 0 is undefined. That's a you're not allowed to do in math kind of thing. Can't divide by 0. Yep.
0 divided by
Yeah, 0 divided by anything will be 0. You can have 0 at the top, right? 0 divided by 4. The answer is 0. So as long as the top of your fraction comes out 0, then the entire thing will come out to 0. So just figure out what makes the top 0. So subtract it. And what would we get for x when we simplify that?
-5.
-5. So if you plug in -5 for x, you get -600 plus 600. That would make the top 0. Doesn't matter what the bottom is. You'd have 0 divided by something, and you'd get 0. So that's how you find your zeros. Okay. So we did everything except the graph. Any questions before I do the graph on any of those? All right, so let's graph it. You can either do the original or you can do the one that we combined. I'm going to use the combined one just because it's easier for me to type that in. So we've got 120x plus 600. And we're going to divide by x squared plus 20x. How many vertical asymptotes did this problem have? How many? 2. Remember, anywhere that you have a vertical asymptote, that breaks your graph. Think of a vertical asymptote as like if you had a piece of string, a vertical asymptote cuts it. If you have 2 vertical asymptotes, how many pieces of graph are we going to end up with?
How many vertical
Yep.
asymptotes?
3. Yep. So with 2 vertical asymptotes, that's like cutting a piece of string 2 times. You end up with 3 pieces. So we need to make sure we can see all 3 pieces on the screen. So we could start with zoom 6, but we already know that's not going to be good enough because I have a vertical asymptote at -20. So I would go maybe -40. Give us a little extra. And then let's just leave everything else for now at the standard -10 and 10. And let's graph it and see what comes up. Okay, well, there's 1 piece. There's 2. And there's 3. So we do see 3 pieces. But I don't think that's a good one, right? We want to see more. So let's go a little further up, right, down, and left. Let's go further in every direction. So let's set this at 40. Let's set this at -25, +25. That looks pretty good. I don't think I went further to the left. It could have gone a little further, but you're not going to see much more to the left. But that's a good window. Okay, so there's your graph, and here was your window. We typed it. Right. Any question on getting that graph? Okay, so you get 2 vertical asymptotes. There's the one at -20, and then the one at 0. It's right there. And the horizontal, it's right there. Now, if we were looking at this graph in terms of the word problem, which part of the graph is the one that actually would make sense. If we start to think of it just about the word problem.
The positive parts.
Yeah, the part that's all the way in the upper right. These two parts in the left and in the middle, they have negative x values, which wouldn't make sense in the word problem. Algebraically, sure, we can look at them, but they don't have any meaning in the word problem. So remember, when you are graphing something, be careful about including negative parts to the answer when it's a word problem. So what I want to do now is let's just zoom into quadrant 1. Okay? So we're not going to focus on the negative part anymore because we're going to talk specifically about the word problem. So let's set our mins at 0, and that's a good sketch. So it says that Sue has 2 hours to complete the trip. We want to find how fast she must travel by car. We're not going to do it algebraically, though. We're going to do a lot algebraically in a little bit. So we're just going to do it graphically. So that blue line represents the time it takes Sue to complete the trip. What do you notice? Like, if you look at that graph, what's it telling you? By looking at it, if that's the time it takes to the time it takes to complete the trip, what is that shape telling you? Yeah.
As x gets higher, as x reaches infinity.
And what's x again? Speed.
X gets faster. Whenever it starts to get closer to 0.
What gets closer to 0?
The time. I don't know what y is. Time.
Y is time. As the speed increases, the time to complete the trip decreases. That's what that graph is telling you. Now they want us to figure out when the time is exactly 2 hours. How am I going to use my graph to figure that out? And we've done this kind of thing before. Yeah. So we could use a table if we knew the speed and we wanted to predict the time. But we know the time and want to predict the speed. So we can't use a table for that. But otherwise, yeah.
I don't know how big the gaps are in the time, but if you just set a line at 2 hours.
Yeah, set a line at 2 hours. All right, let's go a little further to the right. All right, I think it's not the best looking graph there, but we got it. What do we need to do now? Yeah.
Find the intercept.
Right. We're going to see where the 2 hour mark crosses this curve and look at the x value, because the x value is the speed. Yeah.
Is the time the y? So the y-axis
Yes.
is always time, right?
Yep.
Is it always going to be in hours?
Well, in this problem, yes. Yeah. So you will hit 2 hours on the y-axis when the x value, which is the speed, is 46.46. So that's the answer. So let's write it down. To complete the trip in exactly 2 hours, Sue must travel by car at 46.46 miles per hour. Now, they didn't ask this, but what if they said, how fast will the train be going if she completes the trip in exactly 2 hours? What would you say for the speed of the train? Yep.
66.46 miles
Right.
per hour.
We knew the train was 20 faster than the car, so it would be 66.46. So when you get to the end of the problem, just pay attention to what did they actually ask for? The speed of the car or the speed of the train? This one was the car. Okay. Any question on that? Yes?
I wouldn't imagine the graph would be any different for like kilometers.
No, the units wouldn't really matter. It would just be the same type of thing. You do a y1, a y2, and look for an intercept. You do have to make sure though that your units are the same. So if they said like, let's say she had 2 hours and 30 minutes to complete the trip, what would you put in y2 if it said 2 hours and 30 minutes? You're mixing units there. You can't. You'd have to put it in as 2.5. Okay? Because there's no way to type in 2 hours and 30 minutes. It's got to be all hours. So don't mix units. All right, so let me just fix this. So that was graphically. Let's look at solving algebraically. Okay, when we solve algebraically, what we're going to be doing is we're going to end up using multiplication, and we might multiply by a variable. Okay. When you multiply by a variable, that can be a problem. So we're going to see what can happen and what we have to make sure of when we do it. So in solving algebraically, we may, not always, but a lot of times, we may multiply both sides of the equation by a variable. There we go. So that's fine now. So when solving algebraically, we may multiply both sides of an equation by a variable. When we multiply both sides by a variable, what can happen is we make an extra answer that shouldn't be there. It's not that we did anything wrong. It's just because you multiplied by a variable, you can create an answer that shouldn't be there. That answer that shouldn't be there that you created by multiplying by a variable is called extraneous. It's an answer that was created because of the method you used to solve the problem. And there's not really any way around it with this method. Right? It's just something that can happen. So the only way that you know you got an extra answer that shouldn't actually be there is to check it. So we'll always make sure that we check our answers. When you're solving a rational equation, what is usually going to happen when you get an answer that you shouldn't have created is it will cause you to divide by 0. That's how you're usually going to know it's an answer that shouldn't be there. It will cause you to divide by 0, which you can't. So the goal in all of these problems is going to be to get rid of any fractions that we have. So let me show you an example with more numbers first, and then we'll do the same thing with a variable. Let's say we had something like 2x over 3 plus x over 4 is 3x minus 5 over 12. There's a number that we can multiply all three of these fractions by, and if we do, it'll cancel out all the denominators. The number you need to figure out is the LCD, the least common denominator. What's the least common denominator of this, this, and that? So the LCD cannot be smaller than any of your individual denominators. Yeah. 12, yeah. And I'm going to think of 12 as 3 times 3. Okay, but yes, the least common denominator of those 3 numbers is 12. So let's multiply everything by 12. But again, think of it as 3 times 4. So multiply the first fraction by 3 times 4. Second fraction gets multiplied by 3 times 4. And the third fraction gets multiplied by 3 times 4. Okay, multiplying by 3 times 4 everywhere. What's going to happen in that first fraction? 3 times 4 times 2x divided by 3. Yeah?
Will the 4 be distributed?
What about the 3?
You cancel out.
Right, the 3 is going to cancel out. Because you have a times 3, but then you have a divided by 3 in the same problem. Timesing by 3 and dividing by 3 cancel each other out. What's going to happen in the second fraction? The 4 cancels out. You have x divided by 4 times 3 times 4. Well, why would you divide by 4 and then times by 4? They cancel each other out. And then what about the last fraction? What's gonna happen there? Yeah.
Will the 12 cancel out because 3 times 4 is 12?
Right. You have 3x minus 5. You're dividing it by 12, and then you're timesing it by 12. So now let's look at what we have left. We have 4 times 2x. We have positive x times 3, which is how much? 3x. And then on the other side is just 3x minus 5. Right, and we're not going to continue solving it from there. This actually would be, yeah, we could solve it, but it's probably not going to be a nice answer. But the point is now you have an equation that's much easier to work with because there's no fractions left in it. Just bring all your x's, combine like terms, bring all your x's to the same side, and finish solving it. Yeah?
What is the least common denominator? Because I don't get why you multiplied it by 3 times 4.
So 12 is the least common denominator.
Okay.
It's the smallest number that this, and this divide into without a remainder.
Yeah. So then why did you use 3 and 4?
Because that's 12.
Because, okay, just because.
Because 12 was the least common denominator.
Okay.
There's no number smaller than 12 that 3, 4, and 12 all divide into.
Okay.
Yeah, the least common denominator has to be, can't be smaller than any of your individual. Now, if this wasn't a 12, if this was like a 13, well, then it would have been a little bit messier. We would have had to multiply everything by 3, 4, 13. 3, 4, 13, 3, 4, 13. But because 12 was the product of these two, it made the least common denominator smaller to find. Any question on that? Okay, let's try it on this one. So the first thing that you should always do when you're trying to solve one of these problems is factor the more complicated looking denominator and see, is it the product of the 2 on the other side? If it is, then it's going to make finding the least common denominator easier. Just like these two multiplied together gave us 12. So let's try to factor the denominator on the right and see what happens. What would be my first term in each set of parentheses when I factor that?
X.
Yep, we have an x and an x. What about my signs? have a negative constant and, I'm sorry, a negative middle and a positive constant. Yep. They would both have to be what? Negative. And what about two numbers that multiply to give you 3, and they would add to give you 4? Yep. 3 and 1. So when you factor the denominator on the right, is it the product of the two that were on the left? Yeah. So that's going to make finding the least common denominator easier. What could we multiply first fraction, second fraction, and third fraction by to cancel out all my denominators?
That factor.
And what is the, think of it as like we did the 3 times 4 on the other one. What would you multiply by here?
X minus 1 and X minus 3.
Yep, x minus 1, x minus 3. It's exactly what we did before, except it's not numbers, they're variables. So this gets multiplied by x minus 1, x minus 3. This one gets multiplied by x minus 1, x minus 3. And this one, x minus 1, x minus 3. Now, don't do that out because something's going to cancel everywhere. What cancels in the first fraction? X minus 1. So you're timesing by it, and then you're dividing by it. So you got rid of it. What would cancel in the second fraction?
X minus 3.
X minus 3. And what would cancel on the right-hand side? The whole denominator. Because this is that. Now, anything you have left is a distributive property. So just be careful when we do this out. What's 2x times x?
2x squared.
2x squared. And what's 2x times negative 3?
Negative 6x.
Yep. Now here, another thing to be careful with, this symbol goes with that number. That's a positive 1. When we distribute positive 1, does that change anything? No, this time it doesn't, just because it was a plus 1. But if it was a number other than 1, it would change it. So that's x minus 1. And what's on the right-hand side? 2. So now we have an equation that doesn't have any fractions in it. What's the highest exponent in that equation?
2x squared.
Just the exponent itself. 2. When the highest exponent is a 2, what kind of equation is that? Well, it is a polynomial, but it's a very specific one. Yeah. Well, it's squared, which means it's a quadratic. Yeah. And when you're solving a quadratic, what do we always get it equal to? You gotta get it equal to 0. So yeah, now we just solved the quadratic equation, and that's our answer. So what I would do first is combine your x's. Negative 6x plus 1x gives you negative 5x. And how would we bring the 2 over to the left side? Subtracting. And there you go. So now we have it equal to 0. I don't think that's going to be factor. Well, yeah, actually that might factor. Let's try to factor it. So we've got a 2x and an x. What about my signs? Both positive, both negative, or one of each?
One each.
Yep, we're going to need one of each. That might not be the right order. We might have to switch them. And then two numbers that multiply to give me 3. 1 and 3. Let's try it in that order. So we get 2x squared minus 6x plus 1x. What's negative 6 plus 1? Yeah.
Negative.
Negative 5. So we got the middle, and 1 times negative 3 is negative 3. Perfect. So it did factor. What do we do with each of those factors now? Yeah.
Solve them. Like separately.
And how do you solve that?
By like, I'm not explaining. Solve for x.
Yep. Well, right now we just have, how do we solve for x with those two factors? Yep.
Set both equations.
Set the factors equal to 0. Yep. So we're going to get x equals 3. And we're going to get x equals negative a half. Okay, so those are two possible answers, but we have to check and make sure they work. Does anybody see any issue if we try to plug those numbers back into the original problem? If not, then they both work. I'm just making it so you can read the original problem a little easier again.
We get 0 under 1.
What do you mean? Here, let's go. Explain that.
3 minus 3 equals 0, so it'd be 1 over 0.
So yeah, if you plug 3 back in, you get 0 in which fraction?
Second.
The second and
Third.
the third. Both of these would come out to 0 if you plug in 3. So that means, what does that mean about the 3? That's not a solution. What do we call that one?
Extraneous.
This one is extraneous. It doesn't mean I won't ask you for it. I might still say, write down all the answers, including any extraneous ones. But if it's extraneous, just label it. So this answer works. That answer does not. There's 3 things that can happen when you solve a quadratic. You're going to get 2 answers. They could both work. They could both not work. Or one works, one doesn't. Those are the 3 cases. Okay.
If neither work, is it no solution?
Right. If they both don't work, then you label both of them as extraneous, and then you say that there is no solution. Yep. Right. Let's try this one. Always start by factoring the more complicated side and see if it is the product of the 2 other denominators. How can you factor x squared plus 2x? This is just the GCF kind of factor. It's not the 2 sets of parentheses. Yep.
Pull out x. Divide by x. Well, you just pull it out and you get x. And then parentheses. And then x plus 2.
Yeah, x plus 2. So again, the denominator on the right is the product of the 2 that are on the left. So what would we multiply all 3 of those by to cancel out my denominators?
Would you just multiply them all by x parentheses x plus 2?
Yep, they all get multiplied by x plus 2. All right, what's going to happen in the first fraction? X's are going to cancel out. Second fraction? Oh, Mia, what happens in the second fraction?
X plus 2 cancels out.
Yep, x plus 2 is gone. And third fraction?
Denominator cancels out.
What's
The entire denominator cancels out.
entire denominator? Yep. Okay, so remember, you are left with distributive here. So you need to FOIL that out. X squared minus 3x plus 2x minus x, and then 2 times negative 3 gives us negative 6. Here we're distributing positive 3 but it's not a double distributive, it's just positive 3 times x. And what's on the right-hand side now? Just negative 6. All right, let's combine like terms and then see what happens. So we have x squared. Negative 1x plus 3x is 2x. And again, it's a quadratic. So how would we move the negative 6 on the right over to the left?
Plus 6.
Yeah, we would add it. But what happens when you add it? Right, it's going to cancel here and here. So you're not left with a constant anymore, which just made it a lot easier to solve. Now we have to factor that, just like we did the last problem, but it's a much simpler kind of factoring. There's no constant. So all you can do is factor out a GCF. What can we factor out of those two terms? Yep. Factor out an x. And what would that leave you with inside your parentheses? X plus 2. So now we've factored it. What do we do with each factor? Set them to 0. Well, when you set the first factor to 0, you're done. And the second one, you only have one step. What would x come out to for the second factor? Negative 2. Okay, so we got our two answers. Go back up and look at the original problem. What would happen if we try to fill 0 back in? Yeah?
First fraction doesn't work.
And what other one?
And the second.
No, second's
I mean,
okay.
third.
Third, yeah. If you plug in 0, the first and the third will not work. What about negative 2? Yeah?
If you plug it in the second and third, it'd be 0.
If you plug in negative 2 to the second and third denominators, those don't work. So both of these answers are extraneous. Which means no solution. Okay, so this is the case where there is no solution. Okay, any question on that one? So let's look at this one. Going back to the car problem, but this one's worded a little bit different. What's different about how this question is worded? It says, at what possible rates could Sue travel to ensure the total time for the trip is less than 2.5 hours? Yeah.
Is it asking for less than 2.5 hours?
Well, yeah, it's asking at the speed she has to travel by car, so her trip is less than 2.5 hours. How is that different than the way the question was worded the first time? I know the first time it was 2 hours, this is 2.5, so the number's different. But there's also something else very different in the wording. Yeah?
It's looking for a range.
Right, it's looking for a range of answers. It doesn't say that she has to do the trip in exactly 2.5 hours. It says she has to do the trip in less than 2.5 hours. So this is an inequality. So we would start the same way. Okay, I've already got the top part in y1, but what would I put in y2 this time? 2.5 hours. Okay, so there's my graph. There's 2.5. What do you think I would have to do now? Yeah?
You'd have to find where they intersect and then everything below that.
Got to find the intersect again. So if she wanted to complete the trip in exactly 2.5 hours, she would go 34.88 miles per hour. How about if I want her to complete the trip in less than 2.5 hours? What does her speed have to be? Faster than that. Yeah. Anything greater than that speed, and she will complete the trip in less than 2.5 hours. Could it be anything that speed or higher? No, why not?
Because if you go that speed, it would get you to 2.5, and it's asking how can you do it in less than 2.5.
Right. It can't be 34.88 because then she would do the trip in 2.5 hours. She has to be under 2.5 hours. Okay. So Sue must travel greater than 34.88 miles per hour. So 40 miles an hour, 42, 50, 60, any speed that is faster than that, and she'll complete the trip in under 2.5 hours.
And if you were to, the question was like, obviously less than or equal to, you can just pull it from underneath.
Right, if the question was worded so that it says, at what possible rates could Sue travel to complete her trip in 2.5 hours or less? Then it would be greater than or equal to 34.88. But it doesn't say 2.5 hours or less. It says strictly less than.
And will you tell us what decimal point to round on?
Yeah, I would always tell you how many decimal points. Yeah. Generally 2 is okay, but I would, if not, I'll clarify that. All right, so when we're solving rational inequalities, like the one we just did on the calculator, always make sure that you zoom out or zoom in enough so you can see what it is you need to see on the screen. And our book is going to mention something about using a sign chart method. We're not doing the sign chart. So anywhere in the homework that you see, use the sign chart method, you're going to use the graphing calculator. Okay, so make sure you remember that. Let's just try another one on the calculator. All right, so let's try this one. When I type it in on the calculator, what do I need to put in the y1 and y2 that's not written on the board? We don't need this when we write it on paper, but you need it when you type it in. Yeah? Right, you've got to put the top, just like I have right there, you've got to put the top and the bottom in parentheses. If you don't, well, it won't come out right. So divided by 2x squared plus 5x minus 3. So you put everything on the left in y1. What's going to go in y2? 1. And just so we remember which graph is which, we're looking for where the blue graph is less than the red graph. So where is the blue one under the red one? We'll do zoom 6. All right, and let's look at this. So first of all, is the blue one ever under the red one? Mm-hmm. Yeah. Let's look at part 1, 2, and 3. Where does it look like the blue one is under the red one in those 3 pictures? Yeah? Parts 1 and 3, whether it actually crosses, like in part 1, it looks like to me it's staying underneath it, but part 3, it's getting pretty close. It might actually cross in part 3, and we'll have to figure that out. Okay. But part 2, I would say we can pretty safely ignore. Let me just make sure I got everything typed in right. Yeah, all looks good. All right, let's check out part 1. Let's look further to the left on the table and see if the blue graph stays under the red graph. So I'm going to look at values that go to the left. Okay. at negative 25, is the blue graph still under the red graph? Yep. Let's do negative 200. Is the blue graph still under the red graph? Okay. If we start to go out this far, and it hasn't gone above it yet, negative 500, is it still under it? Then it's probably always going to stay under it. Okay, I've gone all the way out to negative 500, and the blue one is still just underneath the red one. So let's start with interval 1. How far to the left can I keep going on interval 1? And I will stay under the red graph.
Negative infinity.
Negative infinity. Now, can I keep going to the right forever and stay on interval 1? No, then interval 1 stops somewhere. It stops at that dotted line. Okay, I'm going to make it easy for you to figure out where it stops. Where does it look like interval 1 stops at?
Negative 3.
Let's try negative 3. And if it does stop at negative 3, what's going to happen when I hit enter? I'm going to get an error, and I do. Okay, so to stay on interval 1, you have to stop at negative 3. So what would I put right here to indicate I can go right up to negative 3, but not include it? Yep.
Negative 3 with the square bracket. Or
Parentheses.
Parenthesis. Yeah. So this covers all the values in interval 1. You can pick any number as low as you want to go, up to but not including negative 3. Okay, so we got that. Interval 2 we don't have to worry about. That's never under the red line, so we're not even going to look at it. Interval 3. Does it look like interval 3 is under the red line at all? The blue. Is the blue under the red? Okay. Let's first figure out, in the blue one, can we go as low as we want and we'll always be on interval 3? Like, can I pick any number as low as I want to go for x and I will be guaranteed to be on section 3? No. What happens if I go too low? Then I go off section 3 and I might end up in 2 or 1. So there's a limit to how low I can go and stay on the 3rd section. That limit is right about there. Where does it look like that limit is? 0.5? Yes, it is. Okay, it's not going to be a weird number to find. It's not going to be like 0.4616 or something. It's going to be easy to find. So we can only go as low as a half, not including it. And let's start going to the right and see what happens. Let's go to 25. Is the blue graph under the red graph? No. So then at some point, the blue one went above it. So I have to stop somewhere. You've got to figure out where to stop. How about at 15? Am I above it?
even worse.
Still above it. Let's try like 8. Still above it. Let's try like 3. Okay, well now I'm under it. So somewhere between 8 and 3, the blue graph goes above the red one. I don't want to keep guessing. So how can I find where it goes above it? Yep. Yeah, just find the intercept. So second calc intersect. And I know it's going to be on the screen because at 8 I was under it. Or no, at 3 I was under it. At 8 I was above it. So it must cross somewhere right in here. Okay. And they cross at 5. So 5 is the highest that I can go and still stay under the red graph. Yep.
Now, look, could you pull the table again? It looks like on 25 it would back down. Why is that?
Yeah, so it might be going back down a little bit. We can keep checking further to the right, but it never comes back down under the number 1. It'll get really, really close to it, but you're right. It does start coming back down, but it doesn't come down enough. Yeah. So it's kind of like, if I really exaggerate it, it comes up like this. So that's 1, 2, 3, 4, and then it goes above it at 5, and then it kind of starts coming back down, but it never comes down enough. So it's right here is the limit. That's as far as you can go and stay under the red graph. But you can't really tell that from the picture. Even if you zoom in, I don't think you're going to see a good picture. Let's do like 0 to 2. Okay, so here's the blue part coming up. You can barely see it, like right there, just by like 1 pixel. It comes up and it goes above 5, and it actually keeps going up a little bit, but then it's going to start coming back down and never go back below 1. Okay, but that does show it crossing a little better. So that's how you write your answer. All right, so any graphical inequalities that say, again, use the sign chart, we're always going to graph it. We're not using the sign chart. All right, so those are the questions for tonight. Okay, that's 1 through 13 odd. And then 20, 22, 24, 28, and 31. So we will look at those questions tomorrow. No new lesson tomorrow to do. And then we'll finish our last lesson this week on this.